This project is sponsored by PCBWay, who provided me with PCBs to help me get these custom arcade joysticks working with the MAME arcade emulator over USB. MAME is a multiple arcade machine emulator capable of running, in this case, old games from the 80s, like these SNK games, such as Ikari Warriors, that used the special Rotary LS30 model number joysticks so that the main joystick can go up, down, left, right to move the character around, but his firing direction is controlled by the position that the joystick is rotated to. So you can be shooting off in that direction, but running backwards, for example. So in the original arcade PCB, this joystick has switches for up, down, left, right, and also this 13-pin harness just for the 12 rotary positions plus ground. So the arcade PCB always knew exactly what position this joystick was rotated to control the firing direction of the character on the screen. But when these kind of games were supported in the arcade emulator, they just simplified it down to 2 keyboard keys so that every time you press 1, you rotate 1 more position clockwise, or you rotate 1 position counterclockwise. So in order to get the real arcade joystick to work in MAME, we need to monitor the exact position and wait for the joystick to move, and then send out a clockwise or counterclockwise keystroke over USB. Then MAME can be happy about the keys that it's seeing pressed, and properly, to the best of its ability, support playing games like this with the real joystick. To keep this whole video a bit easier to follow, my design is really closely based on the Digispark development board, which is essentially an ATTiny85 chip configured with a micronucleus bootloader in it and a few components to give the ATTiny85 USB capability, since it doesn't directly support USB. Here's my schematic, and it looks very similar to the Digispark board. We're using 2 GPIOs to go to the USB data plus and minus pins. We have series impedance matching resistors for the USB data, and the data lines are supposed to be in the 3 volt area, so we have Zener diodes here to keep those within spec. And we have a 1.5K pull-up resistor, which is always going to be on one of the data lines to indicate if this is a high or low speed device. Other than that, all I really have is the 13-pin header that the rotary joystick plugs into. It goes to 4 GPIO, and those pins monitor what's going on the joystick, and when necessary, it'll send out a keystroke over USB to indicate clockwise or counterclockwise rotation on the joystick. Then MAME can detect what we're doing and let us play the SNK games. This would just be plugged in as an extra keyboard device, and we would still have another interface to do the regular joystick up, down, left, right, and any other buttons, but plugging this in adds the extra rotary capability. And since this is all based on the Digispark concept, I need to set up the ATTiny85 the same way, using the micronucleus bootloader and setting the fuses in here to configure the chip. I have other videos I'll link to where I've shown how to get the micronucleus bootloader set up and how to program fuses, but what I'm going to do right now, since I don't actually have a through-hole ATTiny85 chip, I'm just going to take the surface mount pre-configured chip straight off of one of my Digispark boards, put it on a surface mount to through-hole adapter board, and just plug it straight into my PCB, and I'm ready to go, almost. One thing I do need to configure is this PB5 pin. My chips are set up so that this pin acts as reset, so I can't use it as an input the way I want right here until I set a certain fuse and make this a PB5 pin instead of reset. Again, I'll link to any reference information, but basically what we need to do, we don't need a special programmer for this. I'm just going to use an Arduino as an in-system programmer. I'm using Arduino Nano in this case. I'm going to put this chip on a breadboard, and when it's all plugged in, I have to run avrdude on the terminal command prompt on the Mac that I'm using and basically tell it to disable the reset pin and turn this into a GPIO. Once that's done, I can put this chip on my PCB, plug in a joystick, and test it out. As far as how this connector is wired up, even though there's 12 discrete switches on the joystick, I'm only reading 4 inputs, where I've grouped it into 3 lots of 4 pins. I've got a video on that as well, which I will link to. I could actually simplify this down to just 3 input pins and put it into 4 groups of 3 to get all 12. Long story short, it just works out better so that when I have 4 inputs instead of only 3, I can spin this joystick really fast and it can keep up. If I only have 3 inputs, it might get confused because I've gone full circle and it thinks I actually tried to go backwards. It's hard to explain, so I'll link to everything I've already covered in the past, but it's wired up this way because we don't really need all 12 positions in order to decode what's going on. So here in the sketch, the way Digispark works, you plug in the USB device after you start uploading, and it wants to give you 60 seconds to plug it in and get going, and then it will auto-detect and take the program. All this sketch is doing is reading in the 4 switch inputs and having a debounce on them so that they are clean. So every time through the loop, I'm reading in the current state of those switches and then checking, has anything changed and do I need to send out a keystroke? So since I have 4 inputs, I'm basically structuring it as a 4-bit binary number where there's going to be a 1 representing whichever switch is currently pressed and zeros which are not pressed. And then I can just do simple subtraction and other calculations to figure out, has the switch moved and which direction has it gone, and do I need to send out a USB keystroke, either capital R for right or capital L for left in this case, to keep it simple. So with this all plugged in, I have a text editor open so that I can just take USB keyboard keystrokes in from this device. And as I rotate the joystick clockwise and counterclockwise, it's picking up the keystrokes correctly. And it seems to keep up well when I rotate quickly or slowly, so it's able to monitor effectively and it's debouncing properly. I'm not getting multiple keystrokes, it looks like. And now hooking it all up to MAME, it seems to play just fine there as well. So this is an overall success. Thanks to PCBWay for sponsoring this project and helping me get up and running with all these experiments. And thanks for watching.